Other than that, hi, welcome to Computational Applications to Policy and Strategy, or CAPS. My name is Leo. I'm a second year here at SAIS, and alongside with Jonathan and Henry, I'm going to be conducting this workshop, of course, with all of you. And yeah, cool. So let's get started. So the agenda for today is we'll talk about some admin, basically the logistics for the next weeks going forward. Then we'll dive right into the content of CAPS, which is decision making, both in an international context, hey Corey, and sort of in a computational context. And to do that, we'll look at game theory, games, and AI. So game theory basically as a means to formalize decision making, games as an environment to study decision making in, and then artificial intelligence sort of as a means to build agents, intelligent agents that are capable of carrying out decisions. And then specifically today, as well in the workshop in general, we'll focus on StarCraft 2. Some of you may know this. This is a real-time strategy game. And we're going to use that as an environment to develop and test our own agents using Python. And yeah, this is going to be the focus of the workshop. In the end today, we'll also briefly touch on AI policy and strategy, which have emerged as fields to analyze and conceptualize some of the trade-offs that arise if you have these very capable, intelligent agents and they sort of carry out decisions in an international context. And in the end, we'll install the required software for next week, which is just going to be Python. So if you already have that, that doesn't really apply to you. Cool. So let's get started with the admin. Or perhaps before we do the admin, since this is like a fairly small group still, perhaps you should just do a brief round of introductions so that everyone sort of has heard everyone's names. I think that's good. Corey, do you just want to start?
Sure, just name.
Yeah, just name. You can add anything you want to, but...
Yeah. Corey Combs, second year, 26.
Henry Fong, first year IBET.
I'm Alex, here Julian Jackie,
Naomi, second year career studies and tech studies.
You are first year.
Jiang Wei, second year.
Chong, I'm actually applied econ, but I used to be an Asian.
Okay, welcome.
John, middle studies, second year.
James, first year strat.
Matt, also first year strat.
Robin, second year economic.
Max, first year IDO.
Karen, second year last law.
Corey, second year ERE.
Michelle, second year ID.
I'm Tomas.
I'm Jonathan, second year strat and China studies.
Okay, very cool. Thanks for the introduction. I hope we sort of get to know each other better throughout the next 6 sessions. The sessions are going to be always on Friday from 4 to 5 p.m. I try to keep it short. We do have to cover a lot of ground, so we may run 30 minutes over on some of these sessions, definitely next week, where we're going to introduce Python. If you have to leave at 5, I totally understand that. It just may be that on some sessions we just have these extra 30 minutes, but definitely no more than that. I hope most of you have visited this. There is a course website. This is the short link. It's basically on our GitHub. It always has these slides for the next sessions. Right now, this is up to session 3, I believe, as well as all the additional resources, readings, and everything. It's all on there. If you need information, look at the website. If there's something you need and you don't find it there, just reach out, send us an email, and we'll sort it out. How you can contact us. So you can contact me at my J2 email or at the SAIS Technology email for any sort of general inquiries. And then Jonathan and Henry are also going to be co-teaching this class. And you can contact them sort of in their specific area of expertise. For Jonathan, it's going to be coding, and for Henry, it's going to be data mining.
Actually, Henry is a much better programmer than I am, so.
Okay. Yeah, cool. But Jonathan and Henry both have sort of extensive experience in this. Yeah, happy that they're part of this. Cool. So the goals of this workshop are we want to leverage sort of very cutting-edge research on AI, specifically how it is conducted in game environments. And our focus is going to be on not so much understanding or sort of these fancy AI techniques, but thinking about how can we actually implement them in sort of an international relations context. How can these computational methods augment the tools that we have in international relations theory, diplomacy, and strategy? And yeah, so that's going to be sort of intellectually, that's going to be what we're doing in this workshop. What's very important is that this is a workshop, so I hope that this is sort of a package that is valuable to you. You can write a short project at the end of this workshop. Hey, and we'll also in session 6 build and host a personal website through GitHub, which is for free. You don't have to pay for that. So I hope that that's sort of a package that can help you apply for like technical internships or you know, jobs in general. And I know many of you are sort of keen on learning Python, which I think is great. Here it's going to be not the primary object of learning itself, but just a tool. So we're just going to use that to build these agents. And if your primary interest is not so much understanding how, you know, agent-based decision-making works and how it can be implemented in an international relations context, hey, Simon, then I think this is still sort of a great environment for learning Python, because we're going to write like multiple 100 lines of code in total. So that should be good. And again, all of these sessions are prepared, but we maximize value by working as a team, so that's super important. I hope this can be as much a discussion as possible. So I have many questions in here, but please, if something is not clear, go ahead, interrupt me. The focus of this workshop is not on getting through the slides and covering all this content, but sort of on covering your interests and answering your questions. Cool. So please do interrupt me if there's anything that you want to talk about in greater detail, or just reach out after any sessions with feedback. I want to talk a bit about the class project, as this is something that you know, you may be interested in, you may actually end up writing. So this could be how I see it, a short technical report on any sort of the topics that we discuss, or you could actually code something. Examples of the report would be like a memo on constraints of deploying AI systems like in a specific scenario. So that could be like a battlefield environment, that could be negotiation, anything that you feel sort of relates to size. You could also write a report on how StarCraft can be used as an environment to study strategic decision making. Or again, you may end up sort of manipulating or actually building from scratch one of these bots that can play StarCraft 2. And I've also printed out one of the examples of like a short report on deploying AI systems in a specific scenario. It's also up on the website, so you can take a look at that. I'll be adding more templates and examples moving forward, but right now that's sort of the one I have. And we'll discuss this in more detail after session 3. Cool. So again, the readings for this course are optional. It probably helps to do some of them just to have some context going into each session, but I'll make sure that all the knowledge that we need, we build up in class together. There's no specific textbook for this topic, again, because it's this idea of, you know, thinking about how computational methods can enhance something like international relations. That's a very broad topic. It's also a topic where no specific literature exists. 3 books sort of cover the subtopics of CAPS, and the first one here would be Artificial Intelligence and Games by Yanakakis and Togelios, which just, if you're interested in how artificial intelligence and games have sort of co-developed and sort of mutually reinforce each other, then that's a very, very sort of semi-technical, readable overview of this field. It's available online, as all of these resources are. The links are on the course website. If you want to learn more about Python, as we're doing this workshop, then this Practical Introduction to Python Programming by Heinold is sort of a good starting point. It's just very much a plain, comprehensive guide to the syntax of Python, so not so much the concepts of programming itself, but just Python. And then finally, for sort of more the policy side, sort of the ethics of artificial intelligence-based decision-making, this book by Boddington, Towards a Code of Ethics for Artificial Intelligence, is a good starting point. And that's available through the JHU library, so you can get copies online. Cool. So for the overview of the workshop, today is just going to be the introduction to the themes and sort of the background of AI and games. Next week, we'll introduce Python from scratch. So that's where we'll go probably 90 minutes, not 60 minutes. And we'll build up all the knowledge that we need in session 2 for then in session 3 to build one of these rule-based bots that can play StarCraft 2 and actually defeat some of the in-game AI. I'll talk more about what rule-based means later in this class. In session 4, this is actually where we go more into the sort of, what you commonly understand as AI, where we look at how can you actually build a bot for StarCraft 2 that learns. And then in session 5, this is going to be Henry teaching. We look at data mining, specifically how it applies to StarCraft 2. What data can you get out of a game? And in the end, we'll also bring in AI policy and strategy to sort of frame through sort of a more frame the technical work that we have done through this sort of lens of policy and strategy thinking. And in session 6, we're just going to basically create and host the website through GitHub, and then we'll catch up with any of these sort of discussion points that we didn't manage to sort of cover adequately before. Cool. I think that's it for the logistics. Do you have any questions on this? Yeah.
I assume we're not meeting like the week of Thanksgiving? Or
No.
the schedule?
No, actually, we're not. So as far as I can see it, we're going to finish in the first week of December. In total. But since you mentioned this, next week, actually, the Tech Lab has an event also related to this on AI strategy and global ethics with Sarah Sewell, who works for In-Q-Tel. So she's definitely like the voice of authority on this. So we have to reschedule, but I'll be sending out an email related to this afterwards, so we don't have to spend time on it now. Okay, cool. If there aren't any more questions, then we can just dive right into the content. Okay, very good. So what this workshop is all about is really, you can phrase it basically in 2 questions. So the first question is, how can computational methods advance our understanding and practice of international relations? And the second question would be, why is it necessary that the international relations community at large engages with emerging technologies such as AI? So these are basically our guiding themes. So on the one hand, what we want to do is we want to understand how we can implement some of these AI technologies into the tool set that we have as practitioners and sort of scholars of international relations. But then we also want to understand what can we actually contribute as international relations people to framing and perhaps mitigating some of the risks that arise when you have these very capable systems that, essentially make up artificial intelligence. So these are sort of the guiding themes. We'll revisit those questions, but off the top of your head, do you feel like you have any answers to these intuitively? Okay, good. I mean, these are big questions. Probably at the end of the workshop, we may have some more answers, but again, we'll revisit those continuously. Cool, so let's get some context. If you search sort of artificial intelligence and international relations, some of the keywords that you're going to encounter are autonomous weapon systems, economic disruption, human security. So there's sort of a lot of research on how artificial intelligence can enhance human security, then predictive analysis, simulation, surveillance. It goes on, human-machine teaming. So there's a lot of content that relates to this idea of the intersection of AI and international relations. And for all this content, the context seems to be that somehow, either to an extent that is yet uncertain, the rise of artificial intelligence is somehow going to change the configuration of world order. So the conduct of strategy and diplomacy and sort of economics is going to be affected by artificial intelligence technologies, either to on a large or small scale. But global order, sort of the configuration of all these elements is somehow going to change. So that's kind of a bold claim, and I think also something that we're going to look at continuously as we go forward. But that's really sort of the context that we're in here. And this idea of the intersection of AI and international relations, it's not very static. There's going to be many ups and downs. So for instance, right now, there's a lot of hype, which is probably also why we're here doing this workshop. Everyone's thinking about, okay, artificial intelligence is going to change everything and so on and so forth. But probably 5 years in, this may have cooled down a lot. But I think if you sort of extrapolate and you look at sort of a broader trend line, then going forward and looking at something like 2030 onwards, it's definitely clear that you will see a lot deeper integration of AI into international relations and into the global order. Again, but this is sort of my predicted chart here. It's not very accurate, but I just want to show that there's going to be a lot of volatility there. And as I'm sure you're aware that AI sort of sparks a lot of reactions, and there's a lot of examples, but I just want to draw your attention to some of them. So this one is actually by Henry Kissinger, which I think is sort of interesting. He wrote an article in The Atlantic, How the Enlightenment Ends, and he said that the age of reason originated the thoughts and actions that shaped the contemporary world order, but that order is now in upheaval amid a new, even more sweeping technological revolution whose consequences we have failed to fully reckon with, and whose culmination may be a world relying on machines powered by data and algorithms and ungoverned by ethical or philosophical norms. So people like Henry Kissinger, I talked to someone at the Kissinger Center. Henry Kissinger is apparently very taken by AI. So a lot of people like him are starting to think about AI because they see that it is going to have an impact on world order as they sort of know it. But it's not just people like Kissinger. It's actually sort of a lot more people out there in the field are sort of responding to this, what sort of we just call sort of the intersection of AI and international relations. So here, I think this came in the wake of sort of the Facebook crises that Mark Benioff, the CEO of Salesforce, tweeted that the only way through our crisis of trust is adopting a set of core values that allows us to navigate these complex times. We are all now stewards of the ethical and humane use of tech. And then he got retweeted by Jack Clark, who's the policy lead at OpenAI, which is sort of one of the leading research organizations on AI. And he said, I think the only answer AI people are excited about is the emerging competition between AI research labs to staff up meaningful policy organizations. So what these examples are just meant to show you is that there's actually a lot of attention out there on what is happening at the intersection of artificial intelligence and then sort of some policy-related consequences. And to get sort of a more, like perhaps sort of a more detailed understanding of this landscape, this is just a very sort of broad breakdown of some of the companies that are active in this space, so that do work related to to artificial intelligence, but then do that in the context of international relations. So if you just want to break this down really broadly into some categories, then you have the sort of leading AI research institutions, which are DeepMind and OpenAI. So basically everything that you know about AI or have heard about sort of originated here. There are sort of dedicated policy research labs. So you have the Future of Humanity Institute at Oxford, which is very prominent. You also have DARPA, so the Defense Advanced Research Project Agency, which in this case is working very much on explainable AI. The idea here is that you have these very complex systems, and then you have a user who doesn't necessarily have a background in AI, but he has to be able to understand the system, and then you have the system sort of explain itself. And there's sort of a bunch of policy issues related to that, and that's, for instance, what DARPA is working on. On sort of the venture side and partnerships, there's the Defense Innovation Unit, which again, sort of in a strategic context, provides funding to a lot of AI startups. The Partnership on AI, that's sort of like a value-based organization that hopes to ensure that artificial intelligence is developed in an ethically sound manner. And pretty much all of the companies, probably apart from the Defense Innovation Unit, DARPA, are like part of this. So it's incredibly big and has a lot of momentum at the moment. And then there's like a bunch of external stakeholders as well. So the UN is actually also part of the Partnership on AI. I think their focus is specifically on looking at treaties to govern autonomous weapon systems. And Facebook and Salesforce also have dedicated AI policy teams, as well as research units. And then I think the most interesting thing is probably the applications. So you have specifically what we're looking at is like agent-based decision-making, artificial intelligence that, artificially intelligent agents that make decisions. There's no companies yet that sort of has implemented that kind of strain of artificial intelligence, but sort of more broadly, you can look at companies like Palantir, which is a data mining company, which uses sort of many of the artificial intelligence techniques and provides services to like government that kind of originated in the intelligence space. And then Hala Systems, that's a very small startup actually, and what they do is they operate in Syria, and they have a neural network space, an AI-based early warning system for Russian airstrikes. So they have like this distributed network of sensors in Syria, and then every time you hear a jet flying overhead, then the systems can classify that jet based on its sound and can say, it started here, in 30 seconds it's going to be in this city, and then in that specific city, they send text messages to people and say, like, go to your shelter. And then Primer is similar to Palantir, also like a company that originated in the intelligence space and does natural language processing, also using AI. Okay, so this is sort of like a very broad overview of the sort of AI and international relations sector, insofar as that exists. So with that information, and sort of going back to Kissinger's prediction that we're going to enter this environment which, through the rise of data-driven machine-based decision-making and artificial intelligence is going to separate from some of the from the core components of the political order that has emerged in the Enlightenment. Do you think that's sort of a reasonable prediction, or would you disagree with it? Yeah, sure, Robin.
Of course, I think it makes sense because if you look at like what most of the large firms doing, they're really like focusing on mostly big data and like all these kind of data mining issues. So it's quite, like, to me, it's quite clear because even like in international relations field, like when we make like policy decisions, sometimes we have this weird like tuitions on specific issue, but when we look at data, we found things doesn't turn out that way. Then we could make the right decision. So I think this prediction.
Okay, cool. Yeah, I think that's a fair point. And I think, again, we look at Kissinger's article more in session 5. To some extent, I guess no one knows. I guess what's important is that if we look at these issues, we have like a sound foundation of what we're actually talking about. So we have definitions in place for artificial intelligence, because that's essentially going to shape, the kind of conclusions that we come up with. Cool. So let's just do that. Let's look at some possible ways to define AI. And it's actually not that straightforward, as you perhaps can imagine. And sort of the classic textbook, one of the classic textbooks on artificial intelligence, which is by Russell and Norvig, Artificial Intelligence, a modern approach, sort of identifies 4 basic ways to conceptualize AI. So each of these has their respective obstacles. And then what we're going to do is basically choose one of them and use that as our definition going forward when we build and conceptualize these agents. Okay, so you could think about AI as sort of systems that think like humans. That's very broad, but then the question immediately becomes, how do humans solve problems, right? So if you actually think that, okay, my benchmark for intelligence is that I want to have a system that exactly replicates the thought process of a human, that sort of cognitive modeling approach faces the obstacle of how do humans actually think, right? That's not very straightforward, and there's a lot of work that remains to be done on that. So Russell and Norvig sort of discard that based on that reason. And then you could say that, okay, what about systems that think rationally? And then I think that's perhaps, it seems a lot more intuitive. Again, rationally just means, you have a set of beliefs, and then you act on, or you have a set of goals based on a certain set of beliefs, and then you do whatever you need to achieve these goals. So in economics, that would be sort of standard utility maximization. But the problem with thinking rationally is actually that just because you're assuming that I think rationally, it doesn't mean that I always have 100% certainty about an environment, right? And then the problem becomes that it's very hard to formalize that uncertain knowledge, right? So I go into an environment, that environment is uncertain, so all I have is uncertain knowledge about the environment, so how can I think about it rationally? In terms of sort of formal logic that you need to sort of get that system going, that's actually very difficult to do. So again, Russell and Norvig say, okay, that's like a big obstacle, so let's discard that. And then systems that act like humans, which I think is very interesting, and I think that oftentimes if you read about AI, then it's sort of implicitly in the context that, wow, okay, now we have a system that can actually, do what we humans do. It's sort of, it is like us. But that's actually one of the obstacles here, is that how would these systems successfully pass the Turing test? Does everyone know what the Turing test is? Yeah, okay. So Turing test originated in the 1950s by Alan Turing, a computer scientist, and he just wanted to have this operational criteria, very hard operational criteria for how to discerning whether a machine is intelligent or not. And when you talk about a Turing test, what you basically have to imagine is like a phone conversation. On the one hand, there's the machine. On the other hand, there's the human. And the human engages in a conversation with the machine. And then in the end, if the human cannot tell whether he's talking to a man, to a human, or to a machine, then that machine is intelligent and it has passed the Turing test. But the problem here, really, and that's something that I want to draw your attention to, is that this idea of humanity is very much personality-based. So you could think of, you could think of a system that just replicates how a teenage boy talks, and then he always says, "Oh yeah, cool. Oh, good for you. Oh great, yeah, I just want to go skateboarding. Oh, now I still want to go skateboarding." And then that's very easy in a way to replicate, and it's also very believable. But at the same time, it's not a very sound benchmark for intelligence. So that's something that is just like inherent ambiguity in the Turing test. So again, sort of based on that reason, Russell and Norvig sort of discard that, and then we're just left with systems that act rationally. And here the question is just, how can you actually always do the right thing? And Russell and Norvig then sort of say that, actually we can break this always do the right thing down into sort of a set of assumptions which sort of all taken together aren't actually that strong. So then they decide for the systems that act rationally. So basically here, act rationally, that's also what we're going to do when we have these agents. We're going to say that, we have our agents are agents that essentially act rational. So in StarCraft 2, as an example, they would just go in there and sort of maximize their utility. Okay, but a bit more detail on that. So the main takeaway here are the advantages. The properties, I'll just briefly go through them. So rational agency does not necessarily depend on correct inference. Correct inference is sort of rational thinking. So a good way to conceptualize that is that, if you place your hand on like a hard surface, then you're immediately going to move it away, but you don't do so after like a conscious deliberation about, okay, this is hard, now I'm going to decide that this actually diminishes my utility, so I remove my hand to just do it. And then again, you have basically a rational action that did not depend on correct inference. And so also the standard for rationality is clearly defined and completely general. Again, that's sort of utility maximization. And we can sort of weaken this to some extent by saying, okay, we're talking about limited rationality. Actually, you cannot always do the right thing in complicated environments. And the advantages are that we can easily compare with the rational actor approach between AI and non-AI agents. And I think we've all sort of heard this in like econ here at SAIS. So rational agency is not something that sort of requires a lot of explanation for us to be able to understand. Questions on that? Good. So what this rational actor approach means is that essentially when we're talking about AI, we're going to look at one thing, and that is agent environment interaction models. So the really basic framework, and then for like different AI techniques, that framework is going to expand to some extent. The basic framework is that you have an agent that interacts with an environment, and based on the actions taken by the environment, the agent receives observation from the environment. So, I mean, to give an example of that, I'm talking right now in this classroom, so I'm taking an action, and then, I can see a reaction to that, and then I adapt, or I hope to adapt, and that would sort of be the observation that I receive. And one model, sort of, to get into the game theory part here, that I think we're all again familiar with from sort of Econ 101, is the prisoner's dilemma, which is used, obviously, this, throughout international relations to study decision making. And we can actually decompose this into an agent environment model. So let's just do that. And I think, let's just decompose that into like an agent and an environment. And I think then that's sort of the useful thing to do, because what we're essentially going to do is, throughout this course, we're going to compare, how would, for instance, an agent program to play StarCraft relate to the prisoner's dilemma. What would sort of, how come that we use this prisoner's dilemma to study international relations, sort of problems in decision making, and so on and so forth, but not sort of, an agent that plays StarCraft 2. So let's establish sort of a set of categories really that help us to sort of compare across different models, across different agents, and across different environments. So for the prisoner's dilemma, we have these 5 categories: so behavior, lifetime, personality, memory, and strategies. And behavior, again, in sort of classic game theory, is just you maximize your rewards. If this is not an iterated prisoner's dilemma, then the lifetime of this agent is exactly one action. So after it sort of either cooperates or defects, it dies. Personality is homogeneous, so you don't actually think that there's inherent differences between these two players in a prisoner's dilemma. They actually sort of they come from the same set of assumptions. And then memory. So I think this is actually wrong. I was thinking about this, and I think it sort of depends on your assumptions. If we think about sort of classic things that we study with the prisoner's dilemma, which is like reciprocity, then that's obviously based on some kind of memory, right? Because you always want to, like, if the other player defected in the previous period, then now you're going to react on that, which means that you have some memory extending back to the previous period. So no memory, I think. Actually, I think that should say it depends. But then the question is also, how deep is that memory? Like, can you just remember the previous period, or can you actually go back to the game, to the point of time where the game started? Okay, so strategies, again, don't matter if you only talk about one period, but then you can have someone who always defects, always cooperates, just chooses random actions, or plays tit for tat. Right, so the environment is actually more complex, which I think is sort of an interesting thing to keep in mind. So the type here is game theory, positive sum. The gameplay is turn-taking. So the idea is that all you ever do is sort of you make your decision and that's it. There's nothing else that you do. The action space means that there's two possible actions in a prisoner's dilemma, either cooperate and defect. And then those actions result in 4 different environment states. So yeah, you could have a configuration of cooperate, 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 defect, defect, cooperate, or defect, defect. And the rule of transition between states is discrete. So every time an agent chooses a specific action, you change the environment state, and that's sort of clearly discernible. Then we also have rewards assigned to each state. And the reward horizon is instantaneous. So as soon as you take an action, you receive a payoff. The motive information is perfect information. So you see basically all the, you have access to the environment states, the action space, and the rewards. And the mode of action is simultaneous. So both agents, I mean, again, this would sort of depend on the assumptions, but both agents sort of make their actions simultaneously. And again, why we're doing this is just to have some criteria for comparing across environments, which I think is useful then if we introduce StarCraft. Now we have sort of this basic benchmark of, what does an agent environment model look like that is commonly used in international relations. Okay. So the interim conclusion right here at this stage, what I want you to take away is that agents are always conditioned by the environment. I think that's super important, because when we think about artificial intelligence, even in this sort of agent-based framework, we just think about, wow, there's this very advanced thing that can do all these things. But then what we have to keep in mind is that actually what it can do heavily depends on the environment. So the environment is actually to some extent even more important than the agent. And generally, I think there's sort of an inherent danger that from an international relations perspective, if you're sort of unfamiliar with this topic, you go into it, you make a set of assumptions, you perform your analysis, you actually focus so much on the agent and not on the environment. Again, in sort of games can provide very useful and then scalable environments to study the behavior of agents. Okay, so now I want to move into the game side of this, so games and AI. Games and AI have sort of co-evolved pretty much. So right since the sort of early 20th century, or sort of mid-early 20th century, when people started thinking about AI as sort of it is conceptualized today, they also started thinking about how can it be used to like solve games. And then 2 contemporary milestones here. There's actually more than that, but would be IBM. So in 1997, Deep Blue, a chess program by IBM, was able to beat Garry Kasparov, who I think at that point in time was the highest ranked chess player in the world. I'll get to the approach in a second. And then more recently, some of you may know this, DeepMind in DeepMind's AlphaGo in 2016 was able to beat Lee Sedol, also one of the highest ranked players of Go. And yeah, so the interesting thing is that what DeepMind did is actually not sort of pure AI. They actually just had a brute force algorithm that would compute through all the different possibilities, but it didn't actually of the game, but it didn't actually learn to play the game. So the first move that Deep Blue ever made was, or say that the first, when Deep Blue made its first move, it had exactly the same amount of knowledge that it made when it sort of made its last move ever. And then AlphaGo is completely different. So when AlphaGo made its first move, it basically had zero knowledge. But then through playing, it just kind of, it learned how to play, which is sort of, there's more sort of a technical side to it. But I just want to draw this distinction here because it's very important for us. On the one hand, between what is called an expert system, which essentially just applies a brute force approach based on a certain set of rules that are specified, as opposed to sort of this really genuine learning-based system, which is sort of capable of going from 0 to 100. And that's important because what we're going to do in session 3 is basically copying this approach. And then in session 4, we'll sort of look into what how you can sort of replicate sort of a AlphaGo style approach for StarCraft 2. But that's insanely complex, so DeepMind itself is working on that. So yeah, we're just going to look into that. But that's sort of an important distinction to keep in mind. And then those are obviously board games. And right now the trend has shifted to video games. And I just have these two examples here again to sort of show you that this is something that is sort of very much taking place in the present time. So Christy Dennison, who's a machine learning engineer again at OpenAI, she said that for decades we've been working on games like chess and Go, which we've just looked at. And the next step is getting closer to the real world because that's where it can really help us. And then adding to that is Andrew Lone, who is like an engineer at the RAND Corporation. He was actually speaking at SAIS the other day ago, and he said that throughout the history of AI, there has been a focus on strategic games, but now AI outfits are pushing for more complexity in multiplayer online battle games. And these algorithms and environments are a far cry from the complexity of the real world in the fog of war, but then again, so are the war games that we train our commanders in and test our strategies in. So I think what's sort of a common denominator here is that if you look at what Dennison said and what Lone said, is that video games are actually a lot closer to the real world than sort of board games. They can help us understand in more detail how something might play out in the real world. And I think where Dennison and then Lone, obviously, I would assume disagree is what it means that they can really help us. So I would assume Dennison would disagree that war games are sort of a useful application. But yeah, but I think both of them would then say that you have to do this with the utmost care. Sort of going from games to the real world is not something that you should be doing easily. There's like a lot of trade-offs in there. But let's look a bit more at some sort of the properties of like a video game as compared to like a classic board game. So you're going to have multi-objective tasks to reach a goal. So in chess and in Go, right, you just make a move to like really simplify that. But in like a video game, you have to do these, you have to build up, for instance, you're in StarCraft, you have to build up your economy, but you also have to command your army, and then within your army, you have to sort of command separate units. It's sort of this, more diversified environment there. Multiple dissimilar units. I guess you could argue in chess that you also have dissimilar units, but in StarCraft, it's just like literally hundreds. Partial information. So you can never actually see like the entire map, whereas like, you go into a Go game or like a chess game, you just see the board and it's there. Continuous action space and environment is then again, oh yeah, long time horizons. So I think here the idea is that you have very much delayed rewards. So if you build up your economy in StarCraft 2, how does that relate to winning the game? Right now, at that specific point in time where you're doing that, you don't like an agent program to do that would not actually be able to sort of deduce from the get-go to say, okay, this is actually going to help you win the game. So you have you have these long time horizons for reward assignment. And then continuous action space and environment, which is that state transitions are a lot more complex. Because in Go and chess, you always make a move, and then you move your, you move your knight, and then that sort of changes how the game state. But in StarCraft, you send out your army, and they're all doing different things, even when you're not watching. So it's sort of more like a continuous transition from one state to another. And the most interesting thing, I think, and I'm super excited about this. I think this is going. If this actually if there's positive research results on that, then I think that's sort of a great thing. Is team play. So cooperation, agents that are able to cooperate with each other. I think that for sort of looking at applications for international relations and sort of human-machine teaming that's something that's just very, very interesting. But again, and that's also a shift, because in Go and chess, and also StarCraft, actually, you don't have to cooperate. You just have to defeat the opponent. Okay, this is again sort of contemporary milestones in video games. The first one here, DeepMind, was Atari DQN. Basically, their system was able to solve, one algorithm was able to solve, like, I don't know, 80 of these sort of 80s computer games. Then Microsoft has one for Minecraft. Actually, I'm not too sure what their, I have to double check what sort of their current results are. So here, what's interesting is that in 2018, again, DeepMind did this capture the flag game. So I think you can see this here. You have sort of these agents that they're like these flags, and then these agents have to walk through this labyrinth, capture like a flag, and then put it into like a specific position. But then the opponent team can also grab that, like rob you of that flag. And here, this was sort of the first time where you really had cooperation. And that's why it's sort of a hybrid approach here, because within the team, the agents have to cooperate, and then across teams, they have to compete. So that's super interesting. And then something you may have heard about, which is sort of reported fairly widely, is the OpenAI 5 Dota challenge. OpenAI programmed like a very sort of advanced agent that can play Dota. Dota 2 is also like a real-time strategy game. I don't actually know this really well. And they had this challenge where they had it perform their algorithm, which is called 5. 5 consisted of like 5 neural nets, each for one of the agents in the sort of Dota team. They had that compete against more of the like very professional teams, and they were actually able to defeat that. And then they sort of moved ahead at the end of the month into like an official tournament for Dota, and then actually they lost. So just to show you that this is it's very, very hard. And actually, even something like OpenAI, they didn't solve this at their first attempt, and now they're sort of reiterating and trying to improve on that. But so where does StarCraft all fit into this? StarCraft is actually way more complex probably than any of the games we just looked at, including Dota. So DeepMind, after doing the capture the flag thing, after doing Go, is now looking into StarCraft 2 as its next challenge. So that's very exciting, because what we're looking at is essentially the same environment that DeepMind is using sort of to solve its next, to enter the next frontier in artificial intelligence. And here you can see, this is actually sort of this is the view of sort of the DeepMind Python API for StarCraft. We'll talk more about this in session 4, but basically, so this is the StarCraft game. This is what it looks like. And then the agent, so the intelligent agent actually does not see any of this. It just sees this sort of feature abstraction. Cool. So Python for StarCraft 2. It's very exciting that we can do all of this in Python. There's 2 libraries that we are going to use in Python. So libraries are just like external packages that we load into Python to be able to have access to like special syntax that allows us to interact with StarCraft. PySC2, released by DeepMind in 2017, fairly complex and is geared towards building advanced reinforcement learning agents. We'll talk a bit about that. And then Python SC2, which is just a lot easier to use. It's actually fairly simple, which is released by this Finnish student. I don't know how he did it, but he did it. So now we're going to use this in session 3 to build sort of our main agent, and then we look into this in session 4. Okay, I want to give you an example of what is sort of the most simple agent that you can build to win a StarCraft game. And that's actually like a real strategy that is out there that is being used by competitive players. It's called worker rush. So in StarCraft, when you start out, you have this base, and you have, I think, 12 workers. And so the easiest thing, obviously, what you can do, you say, okay, instead of delegating these workers to like mine resources, I'm just going to take all of them and attack the enemy base, right? Obviously, for many reasons, that's not a very smart strategy, because if you lose your workers, you've lost the game, and then the agent cannot reproduce any workers unless you tell it to. Cool. So let's take a look at that. Actually, this, in all the times I've tried it, I lost. So this was never able to defeat the AI in StarCraft. And okay, so we're playing this in difficulty medium. But right now, when I was testing this before the session, it actually won, which I thought was funny. Okay, but now I guess we're going to lose, so I'm going to spoil this for you. Okay, so this is, while this is loading, what you just saw is sort of PyCharm, which is one of these sort of developments that you can use to write Python code. Talk more about that in the end. I'm also always very nervous whether JDU Internet is like capable of
Use Hopkins.
use Hopkins. Is that
Don't
better?
use CU.
Oh wow.
Work
Okay.
Hopkins.
Oh, that's a good tip. Nice. Okay, cool. So now what you can see here is we have, so this is called the sort of Zerg. Zergs are one of the races in StarCraft. And now you can see that right now we've sort of given the, we've given these workers the signal to stop mining resources and just move over across the map to the enemy base. And that's going to take them a while. So actually, like in the program, you can also switch this to like super fast. And we're going to do this in session 3 because we don't always want to wait to like, we don't want to have this play out in real time. But just to show you this is like real time.
So
Yeah.
just really quick. So does the AI like you program like where the enemies are?
Yeah, so that's a good point. Actually, it does. So
This one is kind of cheating because basically it just tells you to send all of your workers to where to look like. They already have like preset locations where like people can be, right? So it just says like go to location 1 because people are going to be there.
Yeah.
Like as the person who programmed this simulation that like it's going to be at location 1. So
yeah, that's true. But I think in general, sort of the way StarCraft works, okay, we lost. That's it. So all our workers are done. If we go back to our main base, then you can see like nothing's happening here. So the algorithm has no further commands it can execute. And then if we wait for like probably 3 more minutes, we can just do that where we sort of discuss Robin's and Jonathan's point. They're going to come and sort of destroy us. Okay, so yeah, but that's obviously to some extent, you don't need to scout the map in this case to find where the enemy is because you have this sort of very clear command, which is just go to enemy start location. StarCraft, actually, if you play this in sort of a 2-player setting, always places the players at the diagonally opposite ends of the map. So to some extent, yes, it is cheating. If you look at like a real-world application, you already have knowledge going into it, which is fine. I mean, this is sort of an expert system. Again, it has expert knowledge. But yeah, I think for StarCraft, you could say that it doesn't matter that much simply because the basic configuration here is that anyway. Do you guys want to see how this base gets destroyed? No? Okay, cool. No, we'll get enough. We'll see enough destruction in session 3, so I'm just going to close this. Okay, cool. And I'm also not going to talk about the code. We'll do that in session 3 and maybe session 2 a bit. Okay, this is just the code. You have this. Okay, so let's start comparing this a bit with the prisoner's dilemma. So the behavior here, again, is to win the game. Lifetime is different. So now it's until defeat, which I guess you could say sort of one game is one iteration. Playing StarCraft 2 and until you get defeated is basically one iteration, and it's similar to the prisoner's dilemma. Okay, but personality, again, that's very asymmetric. We have 3 different races with multiple hundreds of units. Those 3 different races are Zerg, Terran, and Protoss. Terrans are like humans, so we'll play Terran for like the most to get this very close to the real world, right? Memory, again, sort of depends. Actually, the agents that we are going to program in session 3 don't have memory. They're not capable of remembering sort of anything that happened. But obviously, if you have like a more advanced agent, then yeah, there will be memory. And the strategies for StarCraft, there's so many strategies out there. I should have mentioned that StarCraft, there's like a huge esports scene around StarCraft. So yeah, but the basic, so there's many sort of different strategies by these players. The idea is that you have to balance, basic idea is that you have to balance resource management and expanding versus sort of defense. So you want to sort of build up your economy, you also want to make sure that you attack your enemy. So the environment, again, is more interesting. So there's a real-time strategy game, I mentioned that. The gameplay is fast-paced micro-actions and the need for high-level planning. So high-level planning again means you have to build up your economy, and then fast-paced micro-actions would be that individual units within your army are sort of moved around across the map. So the action space is huge. It's 10 to the power of 8. Which that means you need hierarchical actions. Hierarchical actions means that the complex tasks that arise in this huge action space are sort of divided into a hierarchy of subtasks. Okay, so environment states, this is crazy. This is like 10 to the power of 1,685. This is very huge. If you compare it with a prisoner's dilemma, where we actually had 4 here, this is vastly more complex. Again, we briefly talked about this. There's going to be like a continuous transition between states simply because we cannot keep track of all these sort of actions, individual actions that our units perform. And what's very interesting is that if we go back to the prisoner's dilemma, then we know that for every configuration of the environment, for every action taken by the pair of agents, we had a specific reward. So you get 3-3, 5-0, whatever. Here is actually unknown. So from a learning perspective, that's sort of a big challenge because if you do something, you don't immediately know whether it's good or bad, right? You only in the end, you know that after like 30 minutes, you can say, okay, all these actions that I did led me to losing the game. Which of these were good, which of these were bad? That's very hard to discern. So that's like a big challenge, and actually the main challenge for building these AI agents for StarCraft 2. Again, long payoff. Yeah, this is basically what I just said. So the strategy, StarCraft 2, and this is the reason why we're able to, like in session 3, build a bot that manages to defeat like the built-in game AI on hard, is that because sort of building up your economy and sort of these strategic tasks, which are from a computational perspective a lot simpler than sort of this micromanagement of individual units, are way more weighted towards or have a greater influence on winning the game than sort of this micro unit. Mode of information is fog of war, so there's imperfect information. I guess you could just see that Jonathan mentioned it. You don't actually know where the enemy base is. In this case, we did, but there's a lot of uncertainty here. And the mode of action, again, is simultaneous. Cool. This is just, I just put this in here to briefly go back to this idea of sort of the Turing test. This is like a paper by Kim et al. On evaluation of StarCraft artificial intelligence competition bots by experienced human players. So what they did, they had, they just basically looked at, they had a data set of replays of StarCraft 2, and then they showed this to a set of participants, and they told them, like, okay, this is actually like an AI that is playing here. Oh wait, no, I think they actually took AI. Yeah, they took replays of actual bots that play StarCraft 2, and then they showed that to experienced human players. And they had sort of these 5 categories of evaluation. And the interesting thing here that I just want to draw your attention to is that humans, in assessing one of these agents, focus a lot on micromanagement, so how individual units are controlled, and sort of decision-making and uncertainty, so how are sort of trade-offs balanced. And the AI competitions are actually won by bots that, just build up the army, go to the enemy base, don't do anything fancy, but just as sort of this, scale that they get from their macro play are like able to defeat the enemy. What's interesting here is that we have just very, very, to some extent, exclusive areas of focus for humans and the AI in terms of how you would approach this game. And I think that it's just very interesting to see that humans actually look at sort of micromanagement and decision-making. The AI just, always wins, or sort of, if you think about it, sort of evolutionary, just focus on winning the game and sort of its overall performance rather than those two things. Okay. What I want to do now briefly, this is going to be a bit more formal, but I just want to sort of provide you with, going back to this basic model of agent and environment interaction, I just want to show you the respective agent and environment models for like a learning-based agent and a rule-based agent. So here the idea is, so we've already, apart from the reward, we've already seen this, right? So the agent takes an action, receives an observation from the environment, but then in order to be able to learn, you have to know, like, was this action good or bad, right? So you need like a reward. So if there's like a game where it's about, you always walk and then there's like a cliff and you have to jump over the cliff. If you don't actually get negative rewards for like falling off the cliff as opposed to like jumping to the other side, I guess, you would never able to learn anything, right? You would just keep walking and falling down the cliff. So the reward is essential in order to enable the agent to learn. So on top of you have to on top of the observation, you need some you need some reward to sort of discern whether what you did was good or bad. Right, and then this is just sort of across time, obviously. So you do one action, you receive a reward observation, and then it just continues. Questions on that? Okay, cool. What is different in sort of the rule-based system is that actually we just have this sort of, you can think of it like an engine that just tells the agent to do like a specific set of things, and then the ability of the agent to observe things is very limited. So it's actually only going to check. For instance, we could tell, going back to this example that we just saw in StarCraft, we could just also tell our agent to like reproduce workers every time we're below 12 workers because one of them killed, we want to build a new one. And then all the agent would ever observe is that, okay, do I have 12 agents or do I have less than 12 agents? It would not observe anything else about the environment. In a way that makes things a lot more simple and easier to build, but it's also like a big constraint because you just discard a lot of information that the game gives you. Okay. Again, I just want to compare them here because that's important. For the sort of learning-based agent and environment model, the reward enables utility maximization. The utility maximization enables learning. Learning, in turn, enables like dynamic decisions. So you have adaptation. And in the case that we just saw, this would be called reinforcement learning. And then for the second loop, again, we don't have any reward. We don't have any utility. It's just sort of very, very simple. There's no learning. The actions are static. It's not going to change across environments. So no matter what kind of game, if you will, or what kind of map of StarCraft that we're looking at, nothing changes. It just always just checks, okay, do I have these 12 workers? If not, I'm going to build new ones. If I have 12 workers, fine, I'm just not going to do anything. And that's called rule-based. So we just specify the rules. In this case, the rule of checking how many workers do you have. If it's 12, don't do anything. If it's less than 12, build a new worker. Or like enough workers to get you to 12. Cool. So the respective pros and cons, I think this is super important. Something that's sort of worth doing research on in general is that what are actually the differences between like a learning agent and a rule-based agent. So here you can obviously perform a lot more nuanced and complex actions if you're sort of able to incorporate all the information from the environment into your decision making. It's very hard as this requires meaningful rewards. So going back to the challenge of StarCraft, it's actually how do you tell the agent at the very early stages of the game, if you do this, this is actually very good because 30 minutes later it will lead to winning the game. So it's very hard to build up this really meaningful reward architecture to enable learning. But yeah, also again, the agent is going to underperform in sparse environments. So when there's just like no information in the environment, it's very hard to learn, which I think makes sense. And then the actions are like it's super hard to predict those actions. Actually, there's like a separate field in AI research, which is called AI safety, which is basically studies how these systems can become predictable. But for loop 2, the complexity of the agent is obviously constrained by coded rules. It does not depend on rewards. The action is always going to be constant across environments and 100% predictable. And again, so here's where the environment sort of comes in. In theory, learning is always sort of a better approach than rule-based, simply because it yields more complex actions. But it sort of depends on the environment, right? Whether that's sort of a useful thing to do. And here's like a question that I want to ask you, and I think this is something that sort of going down the line is sort of interesting to perhaps explore, like in a memo or like the project. Sort of assuming that you have only limited knowledge about the environment and only one shot at success. Would you either choose like a rule-based approach or sort of a learning-based approach? And then, yeah, it's like a tough question. I'm just interested to see what like intuitively you think you would do. Yeah, Robin.
It's a one-time, so I choose
rule-based.
Yeah, because like learning probably like use stimulation like 1,000 times, like what they did like in chess. That works, but like this is one part of the rule, right? What works.
Yeah, I guess that's also what I say. I think you can sort of flip it and then say, like, if you only have limited knowledge about the environment, how can you actually specify rules for it? Maybe it's better to have something that doesn't require rules and can just go in and learn. But yeah, I think it's an interesting question because you can think about. I mean, this is sort of like a super hypothetical scenario, but you can think about a strategic context, and you have to send you're like in a battlefield environment, and you have to send an agent out there. You don't really know much about the environment, and you have to make a choice between, okay, which system am I going to use? Is it a system that is capable of learning, or is it a system that is based on rules? Kind of an interesting scenario to consider in terms of the trade-offs, but I think, yeah. Good. So to conclude, I just want to bring your attention to AI policy and AI strategy, which, so we just talked about, how do you frame these trade-offs between, having a rule-based system or having a learning-based system. And then AI policy and strategy have sort of emerged as distinctive field to study these trade-offs. AI policy is concerned with sort of the analysis and practice of societal decision-making about AI. So this is more like short-term. And AI strategy is sort of the long-term complement of that, where you look at sort of you have a conceptual analysis of AI developments sort of in a long-time horizon. An example, I guess, for AI policy would something be, for instance, if you look at autonomous weapons, then what should be the mode of information transmission between like a human and the system? What's sort of the optimal way of sort of, building this kind of mechanism of information transmission between human and machine. And then AI strategy would be, you think about, okay, what in like 50 years, I have these incredibly smart machines. How is that going to change how we do international relations? And I think this was on the optional readings for today's sessions. This is sort of taken from a career guide on AI policy and strategy. So there's actually career guides on this. So this is not super obscure. If you may think that it's super obscure, it's kind of not, I think. And they're actually mentioning international relations as like a valuable discipline to do research on this. Which I think is sort of great to know. If we here as an international relations school are actually acknowledged by the AI community to be able to bring valuable contributions to this. Again, something that you may just be surprised to hear. But yeah, I think that's sort of good to know. Cool. So now let me just sort of wrap this up. The challenge that we're facing and that we hope to address in this workshop is that we need to integrate computational tools, both the computational tools and the debate on how we can actually implement AI into international relations thinking. And again, sort of two questions that I just sort of want you to be aware of going forward is, where can we actually identify useful points of contact between artificial intelligence and international relations? And where do you see potential overlap between both fields for applications? Okay, so just to summarize, what we talked about today is that AI is having an increased impact on the global order. So we saw that in Kissinger's comments, it's the comments by Mark Benioff and Jack Clark. And there's a bunch of stakeholders out there who are looking for meaningful ways to respond to this intersection, sort of the problems that arise within it. We need clear definitions of AI to actually mitigate the uncertainty that sort of surrounds this topic. And we decide that the rational actor approach, for like a set of reasons, offers the most explanatory power for the kind of task that we want to perform. Games are very useful for testing these environments, for testing these agents, but again, there's sort of a set of inherent risks involved in that. One of the games with the most strategic depths, so the most complexity, is StarCraft 2. We have two Python APIs that we're going to look at, so PySE2 and Python SE2, to build rule-based and learning-based agents for StarCraft 2 in the next sessions. And yeah, sort of the call to action is that the international relations community needs to integrate all of these tools into its thinking and practice. Cool. That's it. Thank you so much for your attention. If you want to install the software, we can do this right now. Otherwise, for next week, we only need Python. So this is not very difficult to install. You literally just go to this link. And then please do not download Python 3.7, which is the newest version. I think I'm not so sure if it's like an issue. So some of the packages that we use aren't compatible with the newest version because it just has some fixes in there which lead the packages to break. So if you I think 3.7 may be fine. I just want you to be on the safe side, so download anything between 3.6 and 3.7. So that would be 3.66. And then what we're going to do. So for Python, you normally write code in in IDE, so like a text editor basically. I'm using PyCharm, which is sort of a bit more like, I don't know, advanced version of an IDE. If you download Python, you get one with it, which is called idle. I can also show you idle. I think I have this here. So idle looks like idle looks like this. So it also has like syntax highlighting. So if I write for in range 50, I don't know what. Okay, this is going to be I don't know, print. Okay, then okay, I have to save this before I can run it. But okay, let's just. Okay, there you go. So basically what I want to show you is that if you download idle or if you download Python, this is basically going to be the text editor here. You're just going to write code. And this is the actual sort of engine, if you will. This is where the code will get executed. I'm going to use PyCharm because it's, I think, for the purposes of guiding you through this, just a lot easier to use. Yeah, Henry.
Yeah, is PyCharm free, or there's a student
Yes.
year license? Or something?
So I think there's two options. You can either use your student account, your student email address to download like a student-free version of the full version of PyCharm, or you can just download the community edition, which is free in any case, whether you're a student or not. So idle is going to be fine for you. It doesn't have any of the like fancy autocomplete options that like PyCharm has. If that is sort of important to you, you can also use PyCharm. There's like a good video on YouTube, which is also here in the slides, on sort of setting up PyCharm for Python. But I think for next week, idle should be fine. But yeah, let me know if you have questions on this. If the download doesn't work or if you're sort of unsure about anything, just please reach out. Yeah?
What about like Atom or other IDEs in with them?
Oh yeah, anything's fine. Like if you already have your IDE and you've worked with that, that's super fine. Like IDEs are, IDEs are just, they're not going to sort of alter the code we write. It's just sort of whatever suits your preferences. Sorry, I didn't ask for like questions on sort of the other stuff, but if you just have any, sort of, I'm going to be here. Talk to me or ask your questions now, and then I hope to see you next week. Thank you so much for your attention.
This is great. Looking forward to it. I actually have Python 3.7 right now because I'm messing with it, but I can get back to it.